Fundamentals of radiation. This topic introduces the fundamental concept of heat transfer by radiation as one of the main mechanisms besides conduction and convection. Radiation does not require a medium and can occur in a vacuum, making it fundamentally different from the other mechanisms. The main focus of this chapter is to understand the physical nature of thermal radiation and how energy is emitted by surfaces. The discussion connects radiation concepts with engineering applications, especially in high-temperature systems. This basic understanding is essential as a foundation for quantitative radiation analysis. Lesson Plan: Heat Transfer. This section places radiation as a logical continuation of conduction and convection in the heat transfer course. The chapter sequence shows that radiation is studied after students understand medium-based heat transfer mechanisms. With this structure, radiation is positioned as a complementary mechanism that often dominates at high temperatures. The connection among chapters helps view heat transfer as an integrated system. This also emphasizes the importance of concept integration in engineering analysis. Learning outcome. The learning outcomes emphasize both conceptual and quantitative abilities in analyzing thermal radiation. Students are expected to classify the electromagnetic spectrum and understand the Blackbody concept. In addition, the ability to calculate spectral distributions and radiation fractions is a main focus. Surface properties such as emissivity and absorptivity are also key components of the objectives. The final outcome is the ability to apply Kirchhoff's law and understand atmospheric radiation and the greenhouse effect. Heat loss in a vacuum. Heat transfer in a vacuum can occur only by radiation because there is no medium for conduction and convection. In this condition, the rate of heat loss is entirely determined by the surface properties of the object. Emissivity becomes the key parameter that controls how much energy is emitted. This concept is very important for space applications and vacuum systems. This example highlights the unique nature of radiation compared to other mechanisms. Radiation heat transfer. Radiation can transfer energy without direct contact and without depending on the temperature of the intervening medium. Energy flows from a hot source to a cooler object due to the temperature difference. The colder air in between does not stop this process, unlike conduction and convection. This phenomenon is commonly observed with campfires or infrared heaters. This example helps build intuition about the non-contact nature of radiation. Electromagnetic spectrum. Thermal radiation is part of the electromagnetic spectrum and is mostly in the infrared region. This spectrum includes waves with very long to very short wavelengths, such as gamma rays. Visible light occupies only a very narrow band between ultraviolet and infrared. In heat transfer analysis, the main attention is given to the range from 0.1 to 100 micrometers. Understanding this spectrum is important to relate temperature to the dominant wavelength. Check your understanding. Number 1. This section is used to check the understanding of the wavelength range of thermal radiation and its position in the electromagnetic spectrum. The question reinforces that thermal radiation is mainly in the infrared region. By answering it, students strengthen the basic spectrum concept that has just been introduced. It also helps connect basic physics concepts with heat transfer applications. Such exercises are important to ensure the concept is understood rather than memorized. Thermal radiation emission. All objects at temperatures above absolute zero emit thermal radiation. The intensity of this emission depends on the temperature and the surface properties of the object. In a room, continuous radiation exchange occurs among all surfaces. Although often unnoticed, this process contributes significantly to the thermal energy balance. This concept shows that radiation is a universal phenomenon. Visible light wavelengths. Visible light covers only a very narrow wavelength range compared to the entire electromagnetic spectrum. Different colors are determined by wavelength, from violet as the shortest to red as the longest. This information is important to relate visual perception to radiation physics concepts. In the context of heat transfer, visible light is only a small part of thermal radiation. This understanding helps distinguish between visible and invisible radiation. Microwave heating. Microwave heating occurs because electromagnetic energy is directly absorbed by water molecules in the food. The vibration of these molecules generates heat volumetrically, not only at the surface. This process makes heating faster and more efficient than conventional heating. This example shows a practical application of electromagnetic radiation in everyday life. This mechanism also confirms that radiation can interact directly with matter at the molecular level. Correct answer B. Microwaves excite water molecules in the food, generating heat internally. Explanation of incorrect options. A. Heat is conducted from the outer surface to the core of the food. This is incorrect because microwave heating occurs internally by exciting water molecules, not by surface conduction. C. Food absorbs microwave energy and directly converts it into mechanical energy. This is incorrect as microwaves generate heat through molecular excitation, not mechanical energy conversion. D. The magnetron generates heat that transfers to food through convection. This is incorrect because the magnetron produces microwave radiation, not direct heat, and microwaves heat food without relying on convection. Radiation in opaque solids. In opaque solids, only molecules near the surface can emit radiation that escapes the material. Radiation generated inside the solid is absorbed by the material itself. Therefore, radiation is considered a surface phenomenon for opaque bodies. The emitted energy then enters the surrounding gas or vacuum. This concept is important for modeling radiation emission from engineering surfaces. Blackbody versus real body emission. A blackbody is defined as an ideal emitter that radiates uniformly in all directions. In contrast, a real body has an emission pattern that depends on direction. Therefore, the radiation intensity of a real surface is not uniform and depends on surface orientation. The blackbody is used as a reference for the maximum possible emissive power. This comparison helps understand how far real surfaces deviate from the ideal condition. Blackbody approximation by cavity. A large isothermal cavity with a small opening can behave like a blackbody. Radiation entering the cavity is reflected many times and eventually almost completely absorbed. The radiation leaving the small opening represents blackbody radiation. The amount of radiation leaving is proportional to the area of the opening. This concept provides a practical way to realize an almost ideal radiation source. Blackbody emissive power curves show that increasing temperature shifts the peak emission to shorter wavelengths. In addition, the area under the curve increases sharply with temperature, indicating a strong increase in total emitted energy. The Sun, with a temperature of about 5800 Kelvin, has its peak emission in the visible region. This explains why solar radiation is very effective for illumination. This concept links temperature to the spectral characteristics of radiation. Check your understanding. Number 3. This question emphasizes two main effects of increasing temperature on blackbody radiation. First, the spectral peak shifts to shorter wavelengths. Second, the total emission increases significantly with temperature. By answering this, students reinforce their understanding of the relationship between temperature and radiation spectra. It also serves as a natural introduction to Wien's and Stefan-Boltzmann laws. This exercise ensures the main physical trends are correctly understood.
The color of a surface is determined by the wavelength of light it reflects, not by what it absorbs. Light of other wavelengths is absorbed, and its energy is converted into heat. Therefore, a red object reflects red light and absorbs the other colors. This process connects optical phenomena with heating due to radiation. This concept explains why surface color influences its thermal behavior. Blackbody radiation curve. The blackbody radiation curve shows the energy distribution as a function of wavelength for a given temperature. The peak of the curve shifts to shorter wavelengths as temperature increases. The total emitted energy is proportional to the area under the curve. This representation is very important for spectral radiation analysis. With this curve, the relationship between temperature and energy distribution can be clearly visualized. Blackbody radiation energy. The radiation energy emitted up to a certain wavelength is represented by the area under the curve up to that limit. Mathematically, this is expressed as E sub b, 0 to lambda, equals integral from 0 to lambda of EB lambda of lambda t d lambda. The magnitude of this energy depends on temperature and the selected wavelength range. With this approach, the fraction of energy in a specific spectral band can be calculated. This concept forms the basis for using blackbody radiation function tables. Blackbody radiation table. The blackbody radiation function table provides cumulative energy fraction values as a function of the product lambda t. This value approaches 1 as lambda t becomes large, meaning almost all the energy has been accounted for. This table simplifies the calculation of radiation fractions without performing direct integration. In engineering practice, this table is used very frequently for spectral analysis. With this tool, calculations become faster and more efficient. Correct answer: B. The fraction of cumulative radiation emitted below a specific temperature wavelength product. Explanation of incorrect options. A. The fraction of radiation absorbed by the blackbody surface. This is incorrect because blackbody analysis focuses on emitted radiation, not absorption. A blackbody absorbs all incident radiation without reflection or scattering. C. The fraction of radiation emitted in a fixed direction regardless of temperature. This is incorrect because the radiation fraction represents cumulative emission over a wavelength range, not directionality. D. The fraction of radiation that is scattered rather than emitted by the blackbody. This is incorrect because a blackbody, by definition, does not scatter radiation. It emits and absorbs radiation perfectly. Radiation fraction band. The radiation fraction in a specific wavelength band is obtained by subtracting two cumulative fraction values at the limits. The shaded region on the curve represents the energy emitted only within that band. This approach is very useful for analyzing spectral filters or selective materials. With this method, the energy contribution in a certain range can be calculated directly. This concept links spectral graphs with practical numerical calculations. Radiation intensity. Radiation intensity describes how energy is emitted from a point in a specific direction. Its magnitude depends on the surface orientation and the emission angles. This concept is needed to calculate energy distribution in three-dimensional space. By using intensity, the directional nature of radiation can be analyzed in more detail. This forms the basis for non-isotropic radiation analysis. Plane and solid angles. A plane angle measures a portion of an arc in two-dimensional geometry.
while a solid angle measures a portion of a surface on a three-dimensional sphere. In radiation, the solid angle is used to represent the directional spread of emitted energy. This concept helps quantify how large the field of view of a surface is relative to a radiation source. With solid angles, directional analysis becomes more systematic. This is a bridge between geometry and radiative heat transfer. Radiation emission and solid angle. This figure shows the relationship between a surface area element, angles, and solid angle in radiation modeling. Energy is emitted into the hemisphere above the surface. The differential solid angle, d omega, is defined as ds divided by r squared and can be written as sine theta d phi. Integrating the solid angle over a hemisphere gives a value of 2 pi. This representation is important for deriving the mathematical relationship between radiation intensity and flux. Radiation emission and solid angle. Radiation is emitted from a surface element into the hemispherical space defined by the angles theta and phi. The differential solid angle, d omega, represents the emission cone and is mathematically proportional to sine theta d phi. If the entire hemisphere is integrated, the total solid angle is 2 pi. The radiation intensity, i.e. theta phi, may vary with direction. This concept is very important in modeling directional radiation and energy exchange. Check your understanding. Number 5. This question tests the understanding of the mathematical form of the differential solid angle. The key idea is that d omega is proportional to sine theta multiplied by the differential angles d theta and d phi. By answering this, students confirm that the basic geometric relationship in spherical coordinates is understood. This concept is often used in the derivation of advanced radiation equations. This exercise strengthens the mathematical foundation of radiation analysis. Projected area and intensity. The effective radiation intensity depends on the projected area of the surface relative to the emission direction. This projected area is given by A sub n equals A cosine theta. The angle between the surface normal and the emission direction determines how much energy contribution is seen. By using the projection concept, radiation calculations become simpler. This shows the importance of surface orientation in radiative heat transfer. Incident radiation. Incident radiation arrives at a surface from a specific direction defined by two angles. This angle of incidence affects how the radiation interacts with the surface, whether more is absorbed, reflected, or transmitted. This concept is important for analyzing the energy received by a surface. By understanding the direction of incidence, the distribution of received energy can be calculated more accurately. This is the conceptual counterpart of emitted radiation intensity. Radiation flux components. In radiation analysis, emissive power, irradiation, and radiosity are distinguished. Emissive power is the energy emitted per unit surface area. Irradiation is the energy incident on the surface from the surroundings. Radiosity is the total energy leaving the surface, which is the combination of emission and reflection. This separation helps formulate the radiation energy balance in a systematic way. Check your understanding. Number 6. This question reinforces the basic definitions of two important radiation quantities, emissive power and radiosity. By answering it, students make sure that the terms for energy emitted per unit area and total energy leaving a surface are not confused. This is important because both terms often appear in radiation energy balance equations. This exercise also helps build precision in the use of engineering terminology. Correct understanding will prevent conceptual errors in further analysis. Spectral integration. Total radiation is obtained by integrating the spectral intensity over all wavelengths. The area under the spectral curve represents the cumulative emitted energy. This approach allows the calculation of total energy from a complex spectral distribution. This concept forms the basis for the relationship between spectral quantities and total quantities. Without this integration, spectral analysis cannot be connected to the global energy balance. Emissivity, approximation. For real surfaces, emissivity usually varies with wavelength in a complex manner. To simplify the analysis, this variation is often approximated using step functions that represent average values over each spectral band. This approach simplifies calculations without significantly sacrificing accuracy. This method is very useful in practical engineering calculations. It shows the compromise between physical accuracy and computational convenience. Surface emissivity types. Real surfaces can be classified based on how their emissivity depends on direction and wavelength. A diffuse surface has emissivity that is constant with direction, while a gray surface has emissivity that is constant with wavelength. Real surfaces generally do not satisfy both idealizations. This classification helps in choosing an appropriate model for analysis. With this approach, the complexity of material behavior can be systematically simplified. Correct answer C. Emissivity is constant across all wavelengths, independent of direction. Explanation of incorrect options. A. Emissivity varies with direction and wavelength. This is incorrect because this describes a real surface, not a gray surface. B. Emissivity is constant in all directions but varies with wavelength. This is incorrect because a gray surface assumes constant emissivity across wavelengths, while this option describes a diffuse surface. D. Emissivity is constant for all materials at the same temperature. This is incorrect because emissivity is a material property and not universally constant for all materials at the same temperature. This option misrepresents the concept of emissivity in gray surface analysis. Emissivity and direction. For conductors, emissivity tends to increase with angle and reaches a peak before 90 degrees. In contrast, for non-conductors, emissivity may drop sharply at large angles. This shows that the viewing direction strongly affects the radiation characteristics of a surface. This effect is important in the design of radiation systems and in optical temperature measurements. This concept emphasizes that the diffuse assumption does not always hold. Emissivity and direction. This figure visually shows how emissivity changes with angle for different types of materials. The difference in trends between conductors and non-conductors becomes clearer through the graphical representation. This visualization helps connect theoretical concepts with real material behavior. By seeing these trends, the implications for design and measurement can be better understood. Graphical representation is often more intuitive than equations alone. Emissivity and emissive power comparison. A blackbody with epsilon equals 1 emits the maximum possible energy and is used as a reference. A gray surface has emissivity that is constant with wavelength, making it easier to analyze. A real surface has emissivity that varies with wavelength, so its emissive power also varies. In general, the real emissive power can be written as epsilon lambda multiplied by EB lambda. This comparison shows the difference between ideal models and real material behavior. Emissivity versus wavelength. For real and gray surfaces, the difference in curve shapes illustrates that the spectral behavior of materials can be very complex. This visualization helps explain why the gray approximation is often used as a simplification. By comparing the curves, the effect of wavelength on radiation becomes clearer. This is important for high-temperature applications and special materials. Normal emissivity variation. Many materials show higher emissivity at longer wavelengths. Heavily oxidized surfaces, such as stainless steel, have much higher emissivity than shiny surfaces. In general, emissivity also tends to increase with temperature. Each material has its own characteristic trend that must be considered in thermal design. This understanding is important for material selection in high-temperature applications. Check your understanding. Number 8. This question reinforces two important trends in material emissivity variation. First, for materials such as silicon carbide and aluminum oxide, emissivity tends to be higher at longer wavelengths. Second, heavily oxidized surfaces show a significant increase in emissivity. By answering this, students strengthen their understanding of the influence of surface condition and spectrum on radiation. This also connects material properties with thermal design implications. Material emissivity ranges. Different materials have very different emissivity ranges. Vegetation, water, and human skin have high emissivity, close to 1. Building materials, rocks, and ceramics fall in the moderate range. Shiny metals have low emissivity because most radiation is reflected. This classification helps estimate the thermal behavior of surfaces in practical applications. Radiation interaction. When radiation strikes a surface, the energy can be reflected, absorbed, or transmitted. These three mechanisms together determine the radiation energy balance at the surface. The magnitude of each part depends on the optical properties of the material. In many engineering applications, one mechanism may dominate over the others. This concept is the basis for understanding radiation interaction with materials. Reflection types. Reflection can be specular, diffuse, or irregular depending on surface roughness. In specular reflection, the angle of incidence equals the angle of reflection, as in a mirror. In diffuse reflection, energy is scattered uniformly in all directions. This difference is important in radiation analysis because it affects the directional distribution of energy. Understanding reflection types helps model surface optical behavior more realistically. Absorptivity and temperature. Some materials, such as graphite and roof shingles, have high absorptivity that remains relatively stable with changes in source temperature. Other materials, like aluminum and porcelain, show significant variation in absorptivity with temperature. This shows that absorptivity is not only a material property, but also depends on the spectrum of the radiation source. This behavior is important in applications involving heat sources with very different temperatures. This understanding helps in predicting material thermal performance.
Correct answer, C. Each material exhibits unique absorptivity trends, with some materials, like aluminum, showing significant variation with temperature. Explanation of incorrect options. A. Graphite and aluminum maintain constant absorptivity regardless of temperature. This is incorrect because aluminum's absorptivity significantly varies with temperature, unlike graphite, which maintains high absorptivity. B. Porcelain and roof shingles show no significant variation in absorptivity with temperature. This is incorrect, as porcelain's absorptivity is known to vary with temperature, unlike roof shingles, which maintain high absorptivity. D. All materials display high absorptivity at low temperatures and low absorptivity at high temperatures. This is incorrect because absorptivity trends are material-specific. Some materials maintain high absorptivity regardless of temperature, while others vary significantly.
Absorptivity variation. The absorptivity of a surface depends on the temperature of the radiation source incident on it. In general, many materials absorb radiation more effectively from cooler sources than from very hot sources. This occurs because of differences in the spectral energy distribution. This concept shows that absorptivity is not only a function of the material, but also a function of the radiation conditions. This is important in calculating radiative heat exchange between surfaces at different temperatures. Kirchhoff's law concept. Kirchhoff's law states the relationship between emissivity and absorptivity at thermal equilibrium. For a small body in an isothermal enclosure, the ability to emit and absorb energy at the same wavelength is equal. This concept provides a strong theoretical basis for linking these two surface properties. In practice, this law allows the determination of absorptivity from absorptivity data. This is one of the most important principles in thermal radiation. Spectral transmissivity of glass. Glass has high transmissivity in the visible region, almost independent of its thickness. However, in the infrared region, transmissivity decreases as the glass thickness increases. This means that thicker glass absorbs more infrared radiation. This property is very important in building and greenhouse applications. This concept explains why glass can transmit light but retain heat. Greenhouse effect. Short wavelength solar radiation can enter a greenhouse and heat its interior. The interior surfaces then re-emit the energy as longer wavelength infrared radiation. The glass does not transmit this infrared radiation well, so the energy is trapped inside. As a result, the temperature inside the greenhouse becomes higher. This principle is also relevant for understanding the greenhouse effect in Earth's atmosphere. Check your understanding, number 10. This question reinforces the main mechanism of the greenhouse effect, namely the entry of solar radiation and the trapping of infrared radiation inside. By answering it, students strengthen their understanding of the different spectral behavior of incoming and re-emitted radiation. This concept is important not only for buildings, but also for Earth's climate system. This exercise ensures the relationship between material spectral properties and temperature is properly understood. It also links radiation theory with real environmental phenomena. Solar irradiance on Earth. Solar radiation reaches Earth's atmosphere at different angles depending on the position of the Sun. The larger the angle from the surface normal, the smaller the effective intensity received. In addition, the atmosphere reduces part of the energy through absorption and scattering. Therefore, the effective irradiance at Earth's surface depends on both the incidence angle and atmospheric conditions. This concept is important in calculating solar energy potential. Solar energy distribution. The total energy emitted by the Sun remains the same as it spreads in all directions through space. However, because this energy is distributed over an increasingly larger spherical surface, the energy density decreases with distance. The irradiance received by Earth is determined by its distance from the Sun and the area over which the energy is spread. This concept explains why planets farther away receive less energy. It also forms the basis of the inverse square law in radiation. Solar radiation, spectral distribution. Outside the atmosphere, the solar radiation spectrum closely matches that of a blackbody at about 5780 Kelvin. When passing through the atmosphere, certain wavelengths are absorbed by gases such as ozone, water vapor, and carbon dioxide. As a result, the spectrum that reaches Earth's surface is distorted in specific bands. This phenomenon is very important in meteorology and solar energy system design. This understanding shows the role of the atmosphere as a natural spectral filter. Scattering and sunset colors. Air molecules scatter shorter wavelength light, such as blue, more effectively. When the Sun is low on the horizon, sunlight must pass through a thicker layer of atmosphere. As a result, most of the blue light is scattered away, and the remaining light is dominated by longer wavelengths, such as red. This is why the sky appears reddish at sunset. This phenomenon connects atmospheric optics with everyday visual perception. Check your understanding. Number 11. This question tests the understanding of the relationship between atmospheric scattering and the change in sky color during sunset. The key idea is that blue light is removed more, leaving red wavelengths dominant. By answering this, students reaffirm the role of wavelength in atmospheric optical phenomena. This concept also strengthens the connection between the electromagnetic spectrum and visual observation. This exercise concludes the discussion on atmospheric effects on solar radiation. Direct and diffuse radiation. Solar radiation reaching Earth's surface consists of direct and diffuse components. The direct component comes straight from the sun without significant scattering. The diffuse component comes from radiation that has been scattered by the atmosphere. The total irradiance is the sum of these two components. This concept is very important in the design of solar collectors and building energy analysis. Surface radiation interactions. A surface receiving solar radiation also receives additional radiation from the sky. Part of the energy is absorbed, part is reflected, and part may be transmitted depending on the material properties. At the same time, the surface emits radiation according to its temperature and emissivity. The radiation energy balance at the surface must consider all of these components. This approach is important for analyzing surface temperature and energy balance. Absorptivity versus emissivity. Shiny metal surfaces have low absorptivity and emissivity because most radiation is reflected. In contrast, dark surfaces such as black paint or asphalt have high absorptivity and emissivity. Surface treatments such as anodizing can significantly change both properties. This relationship is very important in thermal design and heat control. This concept also reinforces the link between optical and thermal properties of materials. The water cycle in hydropower. This example shows how the natural water cycle can be viewed as an energy system. Rainwater is collected in a reservoir and then directed to a power plant to generate electricity through turbines. After that, the water returns to the environment through natural processes such as evaporation and rainfall. Although not directly about radiation, this example emphasizes the importance of energy balance in natural and engineering systems. It shows that the concept of energy and its transfer applies broadly to many systems. Correct answer: B. The reservoir stores rainwater and provides a controlled flow to the turbines for electricity generation. Explanation of incorrect options. A. The reservoir ensures continuous water flow by converting electricity back to water. This is incorrect because electricity cannot be converted back to water. The reservoir's role is to store and regulate water flow, not to involve electricity in this way. C. The reservoir directly generates electricity without requiring turbines or water flow. This is incorrect, as electricity generation in hydroelectric systems requires the flow of water through turbines, which convert kinetic energy into electrical energy. D. The reservoir evaporates water to complete the natural cycle without any role in power generation. This is incorrect because while evaporation is part of the natural water cycle, the reservoir's primary role in hydroelectric systems is to store and regulate water for electricity generation, not evaporation. References. This section shows that all figures and most of the concepts in this chapter are based on the standard textbook by Chengel and Gajar. This confirms that the material discussed has a strong and widely accepted literature foundation. The reference is also important for students who want to deepen their understanding through the original source. In an academic context, including references demonstrates scientific integrity and traceability of sources. This closes the chapter by reaffirming the scientific foundation of the entire discussion.